Okay, let's do a percent yield calculation to help you with your Grignard lab report. So what I've got right here is a look at the reaction that we did in sort of shorthand. We started with bromobenzene, and in the first step we reacted it with magnesium with diethyl ether. Once we had our Grignard reagent, we reacted it in step 2 with benzophenone to make our adduct, and then finally we protonated that adduct with the addition of acid in order to get our final triphenylmethanol product. Now, you weighed out triphenylmethanol, you weighed out benzophenone, and you had a certain number of milliliters of bromobenzene that you started with. And you weighed out some magnesium also. And you did volumes of solvents and volumes of acid. So, it's clear that the triphenylmethanol is our product, and that is going to be important when we think about what percent yield we got from this reaction. But it's less clear which of these molecules that we need to consider starting with. And it turns out it's benzophenone. Okay, all of the other molecules in this reaction are either in excess or are solvents. Okay, magnesium's a good example. You ground up some magnesium, you put it in the reaction, and there was some still floating around when you were doing your extractions. That was in excess. You also had an excess of bromobenzene to make an excess, really, of Grignard reagent. You wanted a lot of that Grignard reagent. Diethyl ether, that was just a solvent. It's not involved directly in the reaction as a reactant or product, so you really shouldn't use that as a determination for how much product you would expect. And the acid, you just sort of added a bunch of acid to get a certain pH. It wasn't part of these core reactants that generated the carbon skeleton here of our product. So benzophenone was sort of the limiting reagent of this, and it's the limiting reagent that we're going to use in order to determine how much product we should make. And remember, a chemical equation doesn't really directly relate in terms of grams or mass. You can't say 1 gram of benzophenone is going to give you 1 gram of triphenylmethanol, because these things weigh different, right? The benzophenone only has 2 rings. Triphenylmethanol has 3. Therefore, 1 molecule of triphenylmethanol is going to weigh more. So we need to think about molecular weights, and we need to think about moles. And the reaction does let us know that 1 mole of benzophenone is, should give us 1 mole of triphenylmethanol. So let's start here. Let's say that we started with 1 gram of benzophenone. We need to convert that to moles so that we can say, for every mole of benzophenone, we should make a mole of triphenylmethanol. How do we know how many moles of benzophenone is in a gram? Well, we need to know the molecular weight. And we can do that by looking it up, right? The molecular weight of benzophenone is 182.22 grams per mole. Or if we know the chemical structure, we could figure it out pretty close. We've got 13 carbons. Each carbon weighs around 12 grams per mole. We've got 10 hydrogens. Each hydrogen weighs about 1 gram per mole. And we've got 1 oxygen, which weighs around 16 grams per mole. But, using 182.22 grams per mole, we can say we've only got 1 gram. So just by common sense, we know that we're going to have a whole lot less than 1 mole of benzophenone. 1 mole weighs 182 grams. We don't have anywhere near that. So 1 divided by 182 gives us 5.5, about 5.5 times 10 to the negative third moles of benzophenone. So that tells us how many moles of benzophenone we started with. It also tells us our theoretical yield, right? If we start with 5.5 times 10 to the negative third moles of benzophenone, 100% yield, our theoretical yield, would mean we would expect 5.5 times 10 to the negative third moles of triphenylmethanol product, since it's a 1-to-1 ratio. Okay, so that's what I said here, right? Since benzophenone and triphenylmethanol are 1-to-1, we would expect the same amount of moles of triphenylmethanol product, and we'll call that the theoretical yield. So you weighed your triphenylmethanol at the end of the experiment, and you got something that you wrote down in your lab notebook. Let's imagine that when you weighed it out, you got 1 gram of triphenylmethanol as product. Again, you don't really care how many grams you have. You need to know how many moles you ended up with. So just like we did with benzophenone, we find the molecular weight of triphenylmethanol as 260.33, which makes sense. It better be more than the molecular weight of benzophenone because we've added a whole carbon ring to this thing. So 1 mole of it should weigh more. We divide our 1 gram by 260.33 grams per mole, and we find out that we only had 3.84 times 10 to the negative third moles of triphenylmethanol. That's less than our theoretical 100% yield of 5.49 times 10 to the negative third. And so we can use the following equation to figure out what percentage of that theoretical yield did we get. So we take our actual yield, which was based on us weighing 1 gram, which is 3.84 times 10 to the negative third moles. We divide it by our theoretical yield, 5.49 times 10 to the negative third, and we turn it into a percentage. So for this example, we get about a 70.3% yield of product from this reaction. So use the weights that you have, the masses that you determined from your benzophenone and your triphenylmethanol, and see what your percent yield is. Again, there's really probably obvious explanations for why it wouldn't be 100% through all the extractions, separatory funnel work we did. If it's over 100%, again, you probably have some contaminant in there, which is not hard to believe, or it wasn't dried completely so that you're weighing out also some ether or water as part of what you're considering as product.